Chapter 3, Module 2. In this module, we shall discuss two important properties of topological spaces. One is connectedness and the other one is compactness. Among all the properties of topological spaces, connectedness is perhaps the simplest one to conceive intuitively. Our intuition suggests that a topological space is connected if it consists of a single piece. Now, we mathematically formulate our intuitive understanding. A topological space X tau is said to be disconnected if there exists two non-empty disjoint open sets U and V such that X is equal to U union V. The pair U V forms a disconnection of X. A space which is not disconnected is called connected. In the definition of disconnected space, one may also take U and V as non-empty disjoint closed sets. We state a theorem that characterizes connectedness of topological spaces. Suppose X tau is a topological space, then the following statements are equivalent. X is connected, X and empty set are only open and closed subsets in X. If A is non-empty proper subset of X, then boundary of A is non-empty. No continuous function of X into the discrete two-point space is surjective. The following are a few obvious examples of connected or disconnected spaces. If we take any indiscrete space, then it is always connected. The null set and all singleton sets are connected in any topological space. Any discrete space with at least 2 points must be disconnected. Real line, that is real numbers with usual topology, is connected. The space of rational numbers Q with the relative topology from the usual topology of R is not connected. The last example shows that connectedness is not a hereditary property. Now, this theorem gives us the precise collection of connected sets in real line. A subset of R with usual topology with at least 2 points is connected if and only if it is an interval. We state a few important properties of connected spaces. First of all, the closure of a connected set in a topological space is always connected. The union of any family of connected sets, no two of which are separated, is a connected set. The continuous image of connected space is connected. Therefore, connectedness is a topological property. Path connectedness even easier to visualize. If we take a surface and take 2 points on the surface, then we start moving from one point to the other and reach the other point without any break, then these 2 points are said to be connected by a path. if this can be done for any 2 points on this surface, then that surface is called path connected. Now, we shall take this intuitive idea and generalize this concept of path connectedness in the general topological setting. Let X be a topological space. A continuous function W from the closed interval 0 1 to X is called a path with initial point W 0 and terminal point W 1. The topological space X is said to be path connected if for every pair of points x y taken from capital X, there is a path W such that X is equal to the initial point W 0 and y is equal to the terminal point W 1. Note that there is nothing special about the interval 0 1. One may equivalently take the interval as closed interval a b for any 2 real numbers a and b. Now, we define 2 more concepts, locally connected and locally path connected. A space X is said to be locally connected at X belonging to capital X if for every neighborhood u of X there is a connected neighborhood v of X contained in u. On the other hand, it is locally path connected at X if for every neighborhood u of X there is a path connected neighborhood v of X contained in u. If X is locally connected at every point X, then the space is called a locally connected space. Similarly, the space is said to be locally path connected space if it is locally path connected at every point X of capital X. Now, we cite a few examples. Suppose we take any interval in real line R, then it is both connected and locally connected. If we take the subspace closed -2 to open 1 union open 1 to close 2 of R, then it is not connected, but locally connected. Now, if we take the topologist's sine curve, that is the subspace of R2 consisting of the points x y such that y is sine of 1 by x whenever x is between 0 to 1, 1 closed, union the points of the form 0 y where y varies between -1 and +1 closed interval. Then this topologist sine curve is connected, but not locally connected. The rational numbers Q with the subspace topology from R is neither connected nor locally connected. So, we get all possible combinations for connected and locally connected spaces. We state another theorem that a path connected space is connected and continuous image of a path connected space is path connected. We shall see that these two results will be used in our course very frequently. So, we prove these two results. Suppose X is a path connected space. If possible, let it be not connected. Then there exist non-empty disjoint open sets U and V such that x is equal to u union v. Now, we choose one point x from u and the other point y from v. Of course, as u and v are disjoint, x and y are two distinct points of capital X. By path connectedness of capital X, there exists a path alpha from closed interval 0 1 to x such that alpha 0 is x and alpha 1 is y. Now, if we look at alpha inverse u and alpha inverse v, then since alpha is continuous and u v are open in x, alpha inverse u is open in closed interval 0 1 and alpha inverse v is open in closed interval 0 1. Therefore, we get two open sets in the closed interval 0 1 such that alpha inverse u union alpha inverse v is the whole of closed interval 0 1. Now, alpha inverse u must be non-empty because the point 0 is there inside alpha inverse u, and alpha inverse v is also non-empty as the point 1 is inside alpha inverse v. And of course, u and v are disjoint, means u intersection v is empty, thereby alpha inverse u intersection alpha inverse v is equal to alpha inverse of u intersection v, and that is again empty. So, what we are getting is that alpha inverse u and alpha inverse v is giving a disconnection of the closed interval 0 1. Therefore, the closed interval 0 1 becomes disconnected, but we know that in real line a set is connected if and only if it is an interval. So, 0 1 cannot be disconnected, thereby proving that x has to be connected. Now, we prove the next result, that suppose f is a continuous function from x to y, and we know that capital X is path connected. We want to show that its image f x is path connected. So, we choose two points from f x. Let us call the points f a and f b. That means, the points a and b are inside capital X. Now, we know that capital X is path connected. So, there must be a path, that means a continuous function alpha from closed interval 0 1 to x such that alpha 0 is a and alpha 1 is b. So, we get a path joining a and b, thereby f composed alpha 0 is equal to f of a, but f composed alpha 0 is f composed alpha evaluated at 0. Now, we see that f composed alpha is a continuous function from the closed interval 0 1 to y such that f composed alpha 0 is equal to f a, and similarly f composed alpha of 1 is equal to f of alpha 1, that is f of b, thereby it is giving a path which joins the points f a and f b. So, that means any two points in Fx can be joined by a path, proving that Fx is path connected. Now, we define another term called component. A maximal connected subset of a topological space is called a component. In other words, a connected subset of a topological space not properly contained in any other connected subset of the space is a component. If a space is connected, then certainly it has only one component. If we take the discrete space, then every singleton set is connected and nothing else is connected there, and therefore, the components are all singletons. Now, we state a theorem regarding components. Suppose X is an arbitrary topological space, then each x belonging to capital X is contained in exactly one component of X. Capital X is equal to the union of its components. Each connected subset of X is contained in a component of X. A connected Clopin set of X is a component of X. Each component of X is closed. Two different components of X are disjoint. Now, looking at 2 and 6, we can say that a topological space is partitioned by components. We now state a few facts about compactness for general topological spaces. In real analysis, we have seen that closed and bounded subsets of real numbers has a very special property. The property is that every open cover has a finite subcover. Compactness is essentially an abstraction of this property. A collection A of subsets of a space X is said to cover capital X or to be a covering of X if the union of the elements of A contains X. It is called an open covering of X if elements of A are open subsets of X. A space X is said to be compact if every open covering of X contains a finite subcollection that also covers X. In other words, X is compact if for every family of open sets U alpha with X equal to union U alpha, there exists a finite subfamily U beta, where beta varies over a finite subset of the index set lambda of script A, such that X is union of all these U betas. First of all, we know that real line cannot be covered by finitely many open sets from the collection pointed here of open intervals n to n plus 2, where n varies over z. So, real line cannot be compact. The subspace Y containing the points 1 by n where n varies over the natural numbers, union the singleton 0 is a compact subset of R. Any finite set, no matter which topology is given on the base space X, is compact. Any infinite set with discrete topology is non-compact, while any indiscrete space is always compact. We now state a few important results regarding compactness of a space. Every closed subspace of a compact space is compact. Every compact subspace of a Hausdorff space is closed. The continuous image of a compact space is compact. And finally, in case of Euclidean spaces, we have Heine-Borel theorem. The theorem states that a subset of an Euclidean space is compact if and only if it is closed and bounded. Finally, in case of product spaces, we want to see what happens to the connectedness and compactness of the product space given the original spaces satisfying those properties. Now, this theorem states that if X and Y are two topological spaces and we take the product, then the product space is connected if and only if X and Y are connected. Now, one side is trivially true, that since we know that continuous image of connected spaces is connected and we know that the projection maps are continuous, we have that X cross Y connected implies X as well as Y are connected. We can prove that X and Y are connected will imply the connectedness of X cross Y. Similarly, if we take path connectedness, then as expected that if X cross Y is path connected, as the continuous image of path connected spaces is path connected and the projection maps are continuous, we certainly have that X and Y are path connected, but the non-trivial portion is to show that if X and Y are path connected, then X cross Y, the product space, is path connected. And same thing happens for compactness, that if we take the product of spaces, then it will be compact if and only if X and Y, the component spaces, are compact. In developing the course on algebraic topology, we frequently use the concept of connectedness, compactness, path connectedness, etc. There are several important as well as interesting properties of connectedness and compactness, but we have mentioned very few of them which we require in development of our course.